nanohub.org.
Online simulation and more for nanotechnology.
So this is the second class for this analysis of experimental data and design of experiments. In the first class, you may remember that we discussed a couple of things. First one was that data, what is data? And I wanted to emphasize at that point that data is not information. You may know a lot of things, that does not mean that you can use them. Information is something which is contained within the data. So this is very important. And I also explained the difference between small data and large data. By small data, I meant that data that are taken by careful design of experiment. And here, the fewer data that you can use to get and validate an hypothesis, the better it is. So in that sense, the smaller data, in fact, is not inferior data. In fact, it can be a superior data. And then I also explained to you large data. Large data you get from various web services and social media and other things, where you have plenty of data as is. And if you know how to ask intelligent questions, you can get deep insights about various questions, or you can get a lot of answers. So today's lecture, I want to start on that, continue on that discussion, and we want to go back to the basics. Today's discussion and discussion for next two lectures will be all about input, or the data taken as is. And the question we want to discuss is how to collect the data, and more important, how to plot the data. This is still not, we are not going to process the data yet. We are not going to test the hypothesis associated with the data, whether the data is trying to tell a story or not. That we'll ask a little bit later. But we want to start simply by thinking about how to take the data itself and clean up the data. Very important in general. So there will be a set of topics that we will discuss. And this would be, some of them may be familiar to you in terms of the matrix, in terms of statistics. Then we will also be talking about how to think about starting for projection, lifetime projection, for example, and cumulative probability distribution, how to plot those data. And it turns out that there are very special ways you should be doing these things. Then I will conclude after discussing this. Now, the first thing we all know is that there is a distinction between population and a sample. For example, population would be the height of all the people in the United States. If we could get all through a census or something, if we could get all the height of everyone in the United States, then we could answer this question, that what is the average height of a person in United States. But even in census, that's almost never possible. And so what we have to do or rely on is to take a sample out of it. For example, just in this class, we have a few students, and we could take a average of their height and try to see whether they are representative of the total average height or not. And one thing is immediately obvious, that if a country has, let's say, 300 million people, and if there are 100 students in a particular group, we can take many samples of 100 students. So therefore, every time we do a different sample, the result will be slightly different. So first thing you ask about for the sample is what we are putting here as a T on the bottom left is and if you have n samples, so you're talking about n elements within a sample, then if you want to know the average, we generally divide it by n. So for example, the sample size, if it is 10, then n will be 10. Although the original population may contain 300 million, let's say, 300 million people. So getting the average, in this case I'm writing it as time, as t, but it's in general average, because we'll be often be talking about failure time or breakdown time in this class. So I have written it as t, but you realize that the t is just a symbol average symbol. The interesting thing is that if you wanted to know the standard deviation of these samples, then one way we do it is to take every value tj, which is the height of, let's say, individual person, subtract the average value, and then square it. That tells us the variation from one person to another, and then that gives you the S square. But the interesting thing you will notice that in one case, I divide by n minus 1. In another case, if I want to do sigma square, which looks almost like the same formula, but the sigma really depends on when the sample is very large, or population sigma variance, then you can divide by n. But anytime you have a small sample meaning the sample less than 30, in that case, the tradition is to take out minus 1. Now, this minus 1 is very important because every time, why do we take out that minus 1? Is because anytime you are using an information which has already been derived by using some property of the sample. For example, here the average t. We have already used that information and we are putting it in the second equation. So our degree of freedom has reduced by 1. And so therefore, I have to divide by minus 1. And then anytime the degree of freedom, let's say I want to do second moment or third moment, that correspondingly every time I reduce use the previous information to calculate a new thing, then I have to reduce the degree of freedom. So if you started with 10, then we'll divide with 9. The next moment, we'll divide by 8, and so on and so forth. And it's very important that we do so. Now, one of the things that is very interesting is that if you are using Excel, then you can calculate these numbers just in a second. Even better, if you put it in Wolfram Alpha just as a set of numbers, you just throw in numbers, copy paste from anywhere. You can take an Excel sheet that has, let's say, 5,000 numbers. You put it in Wolfram Alpha as a copy paste. It will give you all this information in one shot. In fact, first 15 slides or so, you can get all of them in 2 seconds in Wolfram Alpha. So you'll have the homework. If you try that out, you'll see that it's very easy. Now, it's important to realize that actually this average standard deviation or the third order moment or fourth order moment, these things are sort of an alternate representative of the data. If you had, for example, the height of 30 people, that's in, you just measured the height, that's one set of data. But you could equally well have represented the data with average and standard deviation and second order deviation and third order deviation. If you had all those measures, you could reconstruct the original distribution. It's like Fourier series, that if you have a given time sequence, and you can do Fourier series, and if you could keep all the frequencies, then you can construct back the original time signal, right? So these are sort of alternate spaces. And similarly, the moments of the distribution, if you keep enough of them, how many? That is a question. How many you have to keep. But if you had, let's say, infinite amount of them, in both cases, then you can sort of go back between one and the other. And you will notice the general formula where I have put in the general formula on the right side, where I have written, you see, that K is the moment that you're talking about. When K is 2, then that's standard deviation. When K is 3, that's the cubic, the third moment, and so on and so forth. And have you noticed that in the denominator, I have n minus k plus 1. And that is because that every time I'm using the average into the moment, or the second moment into the third moment, I am actually have one less degree of freedom. So therefore, I have to adjust the denominator by that way. If you have a large number like 100, then this doesn't make any difference. But if you have just 10 samples or 5 samples, then you can immediately see that this will make a difference. Now, this notion of average is sort of a very interesting thing, because before 1600, people didn't like averages. Because before 1600, people used to think that if you are a good scientist, then your data is good. And if you are a bad scientist, then your data is bad. But that the average of a bunch of bad scientists' read results, bad meaning not so precise, that the average can be better than the best was a completely new idea, because the reason is that often the errors cancel out. You can take different people's averages, and Tycho Brahe, the reason he actually got a better orbit is not because he was necessarily had a better instrument, but he essentially took other people's data and averaged it. And when you average it, it turns out this is a very radical concept about how science works, that a bunch of bad things can lead to a better thing. So that was sort of a very interesting aspect. Now, once you have a sample average, remember that we don't have the population. We don't have the height for 300 million people. So therefore, this is a big problem, because if you have just one sample, let's say from this room of the height, and you are asked that, okay, in this room, if this is the height, what is the probability that the height of the United States, the population of the United States, doesn't go beyond a certain range? Let's say in this room, everybody on average, let's say 5 feet 9 inches or something. What is the probability that that the height of the United States population doesn't go above 6.5 inches, let's say? How can you answer that? You have not measured any of them. The remarkable thing is that this is unseen, but yet you can answer this question. That's the remarkable thing about, you measured one sample, and yet you can answer that question. How do you do that? That sounds like a magic. The way you do that is do an inverse experiment. So let's say you have the 300 million people, and you keep, or in this case, let's say I have sent 10K, let's say 10K population, and you go in the, you have actually measured the 10K height. 10,000 people, you have asked what the height is, and maybe Facebook has a new entry, what is your height, date of birth and height, so they have given you 10,000 numbers. Then what you do, I'm explaining an inverse problem, that if you had the information, what would you have done? And then I will go back that if you have one information, how you get back about the 10,000. That's my goal of this slide. So the idea is that let's say you have 10,000 height, and then what you do, you take randomly 20 of them out of the 10,000. So you take 10, 20, first one, 19th one, 272 one, and then you just take 20 of them. And you repeatedly keep taking 20. You keep taking 20. And then what will happen? You will have, for every sample, you will have an average. Every sample, you will have an average, and you plot that average. And the picture that you are seeing here as a look like a Gaussian distribution, that's average. It's not, there is not 10,000 points here, but rather samples of 20, and you have taken many, many samples of 20 out of that. And you can see that what will happen, that most of the time when you're taking the samples out, the average will be close to the global average, the population average, and sometimes you will take only the 20 tallest people, or only the 20 shortest people. And that will be the true tail of the distribution. Now remember that we will not have all of this. What we'll have instead is one sample. And that red arrow can be anywhere. It can be, because you don't know, it can be anywhere. But the remarkable thing is that as soon as you have the red arrow and the associated standard deviation associated with it, you can essentially tell either the black curve would be on the left, like this, the way I have done it, or it would be on the right, because it could be actually a part of a distribution which essentially came from the right. And so therefore, that will give you a plus minus of the range from which, the population from which this particular sample might have been taken, right? And so that it immediately tells you that although you have just one sample, maybe the average height, as I said, is 5 feet 9 inches, but that will immediately, and you also have a standard deviation, let's say 4 inches. that will immediately tell you what is the probability that you have 6.3 inches, or if you subtract a certain amount, at 5.5 inches. You don't have to measure the 10,000 people. That's the magic. And that magic only happens if something is normally distributed or Gaussian distributed, that one sample tells you how things are. We often do that, right? When you took, let's say you are doing things in a rice cooker. We just probe a few rice, and that tells us whether the rice is done or not. And that's sampling, that we don't go and sort of probe every rice in the rice cooker. That will not be very good idea. But you get the idea, right? That's the essence of what we are talking about. And in this case, often we will be expressing things in terms of something called a Z metric, which is mu is the average and sigma is the standard deviation, which we calculated before. And depending on the formula, if you have n greater than 30, then you don't have to take out that -1 or -2 on the bottom. You don't worry about it because the error will be very small. Why 30? Because often we'll be talking about 5% margin. And so 1 over 30 is already around 5%. So therefore, that's where the 30 comes from. 5% significance and all, that's where the 30 comes from. So you will be doing a few examples in the homework, and in 5 minutes, all these things will become clear. Wolfram Alpha will give you these ranges that given the red curve, where the peak of the black curve could be with 95% or 90% confidence interval. All right. Now we are thinking about a sample. My first point today is to say, don't do an averaging. I just did an averaging. But what I'm just going to tell you, don't do that. Because this is what people used to do before computers. Before people knew about the importance of the data, they just used to do things, and averaging is easy. You sum it up and you divide by a number. But don't do that, because as soon as you have done it, you have actually lost the original story the data was trying to tell you. Here is an example. For example, let's say you have a bunch of data points. Do you see that there are given by these blue circles, and there are how many? 2 points on 4. Do you see that? One is around maybe 6.5, another around 9, and so on and so forth. And you have a bunch of data points. The maximum is 30, and the minimum there are with 2, with 4, right? That's what you have. In this case, it is much better to look for median. What is median? Median is something, if you have an odd number of samples, whatever is the one that is in the middle, right? Because you have an odd number, you can have one in the middle. If it is even, then you take the middle 2 and then you divide by 2. So that gives you a number which will be median. Now, median is very important because median is not susceptible to experimental error as much, because you can take this 30 and make it 95. Median will not care about that. On the other hand, if you did averaging, this will immediately, one error will mess up everything. So therefore, median is much more resistant to this type of errors. Now, of course, median is like an average, which is good, resistant to one. What is equivalent to a standard deviation? Well, this turns out that is called an interquartile range. That's similar to the standard deviation. So how do I know this interquartile range? What you have to do is to essentially first define the range. Range meaning that, maximum and minimum value. Then what you have to do, how many points do I have? Can you quickly count? I have 3, 4, 5, 6, 7, 8, 9. Do I have 10 points here? 10 points. If I have to divide 10 by 4, because I want to put it in a group of 4, remember 5 and 6. This is because it's even. 5 and 6 are the 2 points on which I have taken an average. So on this side I have 5, on the left side 5, I have on the right hand side I have 5. So if I want to know the median of the left hand branch, so which point would be the median of the left hand branch? It would be 3. And similarly on the right hand branch, which would be one, it would be 8. Right? 8th one will be the median on that. So therefore, I will put Q1, the first quartile. Quartile means, 1/4 of that. That's what. So I'll put on the third data point, I'll put Q1, and on the 8th data point, I will put Q3. And Q3 minus Q1, I will call it an interquartile range, or IQR. This is a equivalent to standard deviation in the continuous distribution case. But we have a few data points, we don't want to do continuous distribution. And this is again much less susceptible to 1 point moving to 95. It will not change so easily, and that's very important. Now, when do I throw away data is very important. In fact, when you are doing machine learning and other things, it is extremely important to throw away data. Similarly, when you are doing small samples, it's important to throw away data. What should be your criteria by which you should throw away the data? Not because it is not fitting your curve that your advisor said it should fit. That's cheating. But the right way to throw away data is the following. What you have to do is take the interquartile range, which is shown on the bottom layer as the red point, the IQR, and whatever that value, multiply it by, take 50% more. So that will be 1.5 IQR, and add it to the Q3 point, whatever that Q3 point. And similarly, on the bottom side, subtract 1.35, 50% more from the QR, right? So you do that. And once you do that, look at all the points that are within the range. If it is within the range, keep all those data points. Keep all of them. Those are good points. So in that case, you will see that all the blue points and the red point are good points because they fall within that range. But you see the yellow point did not fall in that range, right? Yellow point is larger than this range. So therefore, yellow point would be an outlier. It will be an outlier. One thing is, never throw away a data point. You should plot it in the graph, but you will fit the rest of the points. So outlier doesn't mean you throw it out, because throwing it out is dishonesty, first of all. And second, that outlier may be trying to tell something deep physics about something. You had a different theory, so you thought that was an outlier. A proper theory may actually make that point may be the most important point. So therefore, throwing away data is a very bad thing. You keep the data, but you don't fit it. And on a systematic principle, not which one you like or which you don't like. This is you use it. Now, you see that this is plot is called a box plot. This was invented by Tukey. He was a Princeton professor. All these things happened around 1930s and all. Very important. And you will see in the box plot, there is something called Q2. Q2 is the position of the median. Q1 and Q3 are the two edges of the first and third quartile. You can immediately see that this is saying it's an asymmetric distribution because Q1 minus Q2 is not same as Q3 minus Q2. And you see that there are these two whiskers coming out on the two ends, like cat's whisker, right? So it's like a whisker coming out. But do you see that the whisker coming out on the left edge stops at the red point? The smallest data point is where it stops. The red point is in here, so it stops at the red point. It doesn't go all the way. But on the right-hand side, the whisker stops at 1.5 IQR. It doesn't go all the way to the yellow point. This is what is called a box and whisker plot, and this is universal. So if you plot anytime any data in a MATLAB or in Excel and just choose the whisker plot, you will see this is how it is plotted. All the data are there, the range is there, interquartile things are there, everything is there, except that the distribution shows this way. Now, who told us that it has 1.5 IQR? Why is it not, let's say, 2 IQR or 3 IQR. It comes from the fact that this distribution, you see, if you had a very large sample, then what you could see that you could in principle have a continuous distribution if you had a large sample. And in fact, what that 1.5 IQR shows that it is about 2.7 sigma away of a continuous distribution. And if any of your data point is that far out from the mean, there is maybe something really wrong with that data. Because it's highly improbable that given a sample that your data would be that far out. And that's where this 1.5 IQR comes from. That it says that if you are plus minus 2.7 sigma away, then most probably the data is not probably good, right? That's where it comes from. All right. So I have data. I have plotted, I have blocks plot and all those things. Now I want to do a histogram. Again, histogram is a bad idea. Why bad idea? Just like average, depending on what you want to show. If you take the size of the histogram different size, the curve may go up, down like that, or it may go like that. So you can show any plot that you want if you just simply add up the things. And adding up things randomly is not a good idea. So therefore, we have to do something that is called stem and leaf display. Again, this is in all softwares. If you look at it, all softwares have this stem and leaf display. So how does it work? Assume that you have a bunch of data starting from 444 to 106. There are 17 data points. So let's see. First of all, do you see that what I'm going to show you, if you turned it 90 degrees, it begins to look like a histogram? If you turned it 90 degrees, whatever I'm going to do. So it is like an histogram. So what is done? In the stem, what you do is you take this 4, 4, and then 6, 5, 6. So you write in the stem. It's like a tree. In the stem, you have written 4, 5, 6, 7, 8, 9, and 10. You have written that. Why have I stopped at 10? Because the last number was 106. If the last number was 126, I would have added 11 and 12, right? So now everybody who has a 4 in the beginning, who are those people? I mean, you have 44, 46, 47, and 49. I put that 4, 6, 7, and 9 in the leaf. And is there anything on 50? No, there's nothing on 50, so I don't put anything over here. And so on and so forth. So this one will, you see, although this is looks like a histogram, I can reconstruct the original data with no loss of information because every information is already here. So this would be very good because it has no loss of information. But you can ask, how did you know to put 4, 5, 6 and like this in the stem? Because that is the size of the histogram, right? Why didn't you put something like in groups of 20? You could have done that one also. So it turns out that there is a rule. I will not prove that rule, but there is a rule like this. So let me quickly tell you how it is done. By the way, when you put it in any software, they will automatically do the rules and plot the stem and leaf, but it is done this way. So what you have to do is to take, what is n? N is the number of samples and n is 17 here. So you have to do 10 log 10, 17. And if you do that, 17 log of 10 of 17 is on the order of 1, right? Little bit more than 1. So if you multiply with 10, then do you see that it will be on the order of maybe 13 or so, right? So this is the value of L. So you have to take the near and then the size, which is this, whether you have to take 10 or 15 or not, it involves the second formula, which is range. What is range? 106 minus 44. That's the range. L divided by 13. And you have to see what powers of 10 will give me the value. And in this case, if you do this, you'll see it is about 4.77. And if you do that, you will have to round it up to the nearest 10. And that will tell you what your stem values have to be. You do a few of these practices, then it will become clear. It's sort of difficult to explain directly with this in a PowerPoint, but you get the idea, right? All right. Now, it turns out that the more general version, if you must do an histogram, then it turns out that your histogram should represent the data most closely. So, let's say f is your function and fn of x is your histogram. Your histogram should be such so that your error between the histogram and the original data is minimized. And then people have done this type of things, and that also gives them the size of the histogram. There are different sizes. N is a sample size, and so you put the sample size. This is the standard deviation. This is for continuous data. Do you remember IQR? What is the IQR? It was interquartile range. And so if you have discrete data, you have N and you have IQR. And so the statisticians have very definite formula for putting in the histogram. It's not in your control. If you do it on your own, then you can do anything you like, but what will happen that it will not represent the original function properly. And so therefore there will be a lot of errors. So you calculate that, and that becomes your size of your histogram. All right. Done, right? So you know how to do histogram now. You are going to high school all over again. How to draw a straight line? Do you know how to draw a straight line? And it turns out that straight line is also very easy, but this is a type of straight line you have never seen. Right. So let me explain how to draw this straight line, because this is not the way we learned how to draw a straight line in our schools. Assume that I have 9 points and I want to draw a straight line. This is called discrete statistics. That was what I'm trying to tell you. Now, it don't have to be 9 points. It could be, let's say, 90 points. But the first thing is to group in a group of 3. If you say straight line, then how many unknowns do you have in a straight line? Ax plus b, 2 unknowns, right? So how many minimum points I need is 3. If it is a second order equation, the minimum points I need is 4. Minimum points I need is 4. So if you want to fit a straight line, then all the data that you have to group it. First, you have to group it in 3 groups. If you have 90, then each group should have the green group, the blue group, and this salmon group. So these 3 groups would have 1/3 of the total data points. That's what you'll have. Then within the group, what you have to do is, you see, here I have just 3 data points. You have to take the median. What is the median? In the x side is this location of this is the median, right? Of this point, and this point. If you all project it into the x-axis, this would be the median, because this is 3 points, it would be the median. And similarly, of these 3 things, what would be the y-axis? Y-axis median would be the y-axis of this curve. What I was trying to tell you that, let's say here I have 3 points, but as I said, if you had 90 points, there would be 30 points in here. But let's say I stay with the 3. So you know the median of the 3. The median of the 3 in the x side is this point, because you have 3 odd number median. And so that will will record its x-axis. And similarly, of these 3 points, the median on the y-axis is this y-axis is the median. So you take those 2 values and create this star. And you do that for every one of them, every group. If it is a straight line, then you have 3 groups. If you have to fit a parabola or a quadratic thing, then you group 4 groups. And you follow this. And then you draw a straight line through that. That's how you draw a straight line. And it turns out, again, you can see that it will be very resistant to random errors, because this point can move up and down. This could care less. And yet, in the normal way we do it, least square, change 1 point, you are in trouble, because it can move, the slope can move arbitrarily. It will not be doing that in here, right? The point is, in small samples, you can have fluctuation, you can have error. Your conclusions should not be so dependent on few things in here. And you can very quickly, I'm not going to show you all those, but if you, as soon as you have calculated this right or the middle or the left points, and if you put it in here, you can calculate the intercepts and all other things, because you have 3 points. So this is very, very easy to do. Again, if you ask the softwares that they should do this type of discrete straight line fit, they will give you this curve. So let's say this far, up to this far, we have said about, what is the histogram. We have talked about straight line or curved line. Now I want to tell you about distribution functions, how to plot distribution functions. Let us say that you have 5 transistors and you are working in a company like Intel, and you are a reliability scientist. And that means that you have taken those transistors and applied a voltage and seeing when they fail. Now it can be anything. It doesn't have to be transistor. It can be any failure. You may have bought some phone, and 5 of friends have bought phones, and the phones maybe stop working at a different time. So it doesn't have to have any specific thing. And those failure times are T1, T2, T3, T4, T5, 5 points. Now, if you wanted to do a cumulative failure, then the way you would do it is you can do it in various ways. So therefore, let's say somebody's phone broke after 2 months, somebody's phone broke after maybe 5 months, and somebody's phone broke after, let's say, a few years. So if you have to do a cumulative failure distribution, how would you do it? You can do it in many ways, but let me tell you the one way to do it. One way is to say that when the first device fails, how many devices did you have? 5, right? So the first one failure is 1 over 5. This is 1 over 5. Then you can have 2 over 5 and 3 over 5 and all sorts of things. You can have that. Or you can write I over n plus 1, that 1 over 6. Whatever is the number of samples, you add that 1. For example, in this one, after the first one fails, you have 1 over 6. So it jumped up by 1 over 6. Then you'd go in 2 over 6 and so on and so forth. Right? Every time one failed, that you have jumped. Now it turns out that these formulas are dangerous. It cannot be used like this. Why? Because you see, up to this point, these are all zeros. And often, if you have different probability distribution, there's something called a Weibull probability distribution, for example. That requires you to take log of this. And if you put a 0 here, you will be in trouble, right? Because log of 1 is how much? Log of 1 is 0. And if you have taken a second log, you are in trouble because it will go to minus infinity. So clearly, this way of doing things will not work. So what should you do? What should you do? It turns out that there is a much better formula, and it's called a Hazen's formula, that the way you have to plot it, you have to subtract something called an alpha, Hazen factor, and 2 alpha plus 1. This is derived. So I'm just going to use it, but and explain it why it's so important. But in general, this is already always defined, and this will not suffer from this going to infinity problem, right? In terms of discrete data. If you have millions of data, then none of these things really matter, but you don't. And so therefore, it's very important. Let us say a population has 25 samples, 25. Instead of 300 million, let's say 25. And if you could really take all the 25, then you will have some failure like this. And in that case, whether you do I over n or you do I n plus 1 makes almost no difference. The trouble happens when you have 5 devices and you have to represent what happens to the 25. Remember a few minutes ago I was saying 100 people's height, 300 million people's height. You have to predict one from another. So you see, in that case, the 5 is like a congressman. Because this 5, this is when the first one failed, the second one failed, third one failed, and so on and so forth. This 5 is representing that there is 5 more people. So 5 is really, in principle, they could have, if you took some other sample, it could have been anywhere between this range, in principle. Similarly, this 5 is really this one is representing this 5. And so this I divided by n gives you the upper envelope of where things can be. It is sort of, anytime you use that formula, it's sort of giving preference to the last point. Last point. On the other hand, if you do the other formula, I divided by n plus 1, it gives preference to the smallest point, right? So you can see that is as if you have 5 people, it does things for the poorest, one represents the poorest, the other one does the richest within that group. And which is no good, because you statistically, that's not a good representation when you represent one and the other. What would be the right thing? The right thing would be if you could sort of make a determination that at what point you should jump so that it truly represents the group it is supposed to represent. So in that sense, it is analogous to a congressman. Congressman should not be leaning extremely to the left or extremely to the right. It should represent the population associated with it. And if you do that, that formula that I showed you, Hazen's formula, does that. There's a deep derivation of all those, and I'm not going to show you that, but I'll refer you to and also the slides I post, it will have the derivation, but you can ignore it for the time being. For the time being, simply use this formula, I minus 0.3, n plus 0.4, and that will automatically give you the right answer. All right. Is it clear to you then, hopefully, that how to then draw when you have this cumulative probability distribution? You should always be using Hazen's formula rather than using one or the other extreme formula. Now the next part. This is a little strange. Let us say you have 5 of your friends have bought iPhones. Friends are very rich, so you have bought iPhones. And the first person's iPhone has stopped working after a certain period. The second person's iPhone has stopped working after a certain period. But the third person has lost his iPhone. Now, it was true that up to that point he or she lost it, it was working. So if you wanted to know about its reliability, how do you account for the fact that you really do not know that when the phone would have died, but you know that it survived up to a particular point. And then you have your fourth friend and none of them lost it, and so you know what the failure time is. When you have that few a sample, you have to be very careful about how you draw the cumulative failure. One way is to ignore your friend who lost your data, lost the phone, because it doesn't count, that type of thing. But that would be wrong. So I want to show you how to think about it. Again, I'm using Hazen's formula, but how do I handle incomplete information? Then that's what I want to tell you. And if you have to do it, you can say that if all the formula were there, then I could do I n plus 1. Instead of writing this, I'm just, so that I can save some space, I'm just using this formula just to explain the concept. You can do I over 5 friends plus 1, 6, 1 over 6, 2 over 6, and so on. I told you that this is not exactly right, but I want to get you the concept in place. But because one of your friends lost the phone, so therefore you can say, I'm going to ignore that person. And so now your sample is 4. So you have 4 plus 1, 4 plus 1, and you have 1, 2, 3, 4. This is not right, because up to the point your friend, you're not accounting for this friend. When you have large amount of data, this friend doesn't count. But when you have a few amount of data, this friend counts for a lot. So there are different ways. One, in the very beginning, when the statistics was not done in a sophisticated way, people say that, okay, I'm going to have 5 people, because five people bought the phone. The first one will be 1 over 5, right? The second one would be 2 over 5, but the third one lost it, so I'm still going to keep 2 over 5. 4 samples, but I am going to have 2 over 5 because up to that point it did not fail. Then 3 over 5, then 4 over 5. And what this is going to do is to take this and make this one the distribution. Because there are 2 which has point at 0.4. So therefore, these 2 points are at 0.4. Both of them are 0.4, right? Take a look. For example, the second and the third both have the same value. And then again for the fourth, you again have a jump, right? This is not correct. It turns out that if you do it this way, you'll make a significant error. This is sort of a poor man's way of doing it. The formula that you have to use is called the Kaplan-Meier formula. This is the right formula. Now, this formula is actually very simple. It looks complicated. Remember that alpha was in the Hazen formula 0.3 or so. If you said, just for the sake of clarity, if you said alpha equals 0, the formula will immediately become clear, and I want to explain that to you. All you have to do is to explain. So all you have to do in this case, you have to take n plus, before the failure you have 5 samples, before the failure you have 4 samples, and so therefore correspondingly after the failure you have 4. And in the next class maybe what I will do is I will explain to you that how these ones are calculated based on this formula. It will give you slightly different probability distribution, but that probability distribution is statistically significant. Let me wrap it up. I'll show you some examples, but let me wrap it up with 2 statements. One is that in the MATLAB, there is a one sentence. It will immediately give you the measurements, the values that you want to take, and the ones that were incomplete, the friends who lost their phones, is marked by 1 and 1, and the people, the ones that work properly was the 0, and that says the censored data, and you take all the data associated with it in another array, and in one line you can do all this. You don't have to do anything on your own. So let me wrap it up. So the first statement is that you have to treat the data with respect, right? Don't try to take average or histogram immediately. Non-parametric data analysis means that you don't try to get average or median and other things. That's very important. And the plotting of the cumulative distribution function, I showed you 2 approaches, right? Hazen formula and Kaplan formula. Those things are very important for plotting of the cumulative distribution function, right? So I'll stop here because I know that the music is on, but in the next class we will continue on this.